Okay, so we're continuing our lecture on our introduction to nuclear chemistry. And last week we talked about the ways that nuclear chemistry is different from the regular chemistry that we've been doing throughout the rest of this semester. We talked about the composition of the atom and the particles that are in our nucleus here. And then here are some properties of nuclear reactions that you guys need to know. All right. And you guys did do your, hopefully you did this first section on your in-class activity sheet here, where you were counting the nucleons, and you can determine from this kind of notation how many protons, neutrons are in the nucleus of each of these atoms. You guys feel really good about that? Excellent. Excellent. Okay. All right. Apparently I've got some problems with my zooming, so I'm just going to stay zoomed in here just a little bit. All right. There are a few other particles that we want to define before we move on, just so that we can recognize them easily, because they're going to be in a couple different types of nuclear radiation that we're going to see. So we've already seen the electron. We know that it has a mass of 0, charge of -1, and it resides in that soft cloud surrounding the nucleus. We're going to use this symbol for the electron. So the little e stands for electron, 0 on top, because the mass always goes on top, and electrons have a mass of 0. And now what we see is that in the bottom left-hand corner, instead of putting just the number of protons, what we're going to do is put the number of positive charges. So if your proton then gets a 1 here, then your electron here gets like a -1, because I have less than 1 positive charge, if that kind of makes sense. Following the same notation, the neutron gets a 1 on top because it has a mass of 1, and a 0 on the bottom because it has no protons, no positive charges. And then the proton has a mass of 1 and a charge of +1. Does this notation make sense to you guys? Are you following me here? When atoms decay, there are multiple ways that they can decay. One of the ways that we're going to talk about shortly is by alpha emission, or alpha radiation, and that is releasing alpha particles, which are actually, they have a mass of 4 and a charge of +2. So the element with 2 protons is helium. So an alpha emission is just emission of a helium nucleus. Okay, so this is an alpha particle, is 4,2 helium, same thing. And beta emission actually is emission of an electron. They named this before they knew what electrons were, so they called it a beta particle. So sometimes you'll see this called as a beta minus, to say that it's beta emission and it has a negative charge. Okay. And in addition, we've got a particle called a positron, which looks a lot like an electron. It has the same mass, but it has this opposite charge. So we give it the same symbol because it's the same size and has the same mass as an electron, so it still gets the E, but it has a little +1 down here instead of a -1. This is beta, also known as beta plus emission. So if you see beta minus or beta plus in your homework, that's what it's referring to specifically, both of these. Gamma radiation is not a particle itself, it's just pure energy. We'll talk about that in a bit. But a lot of these reactions release a lot of energy, as we talked about last week. And so sometimes it's useful to say, hey, by the way, there's a lot of energy produced in this reaction. Okay. All right, so let's look more specifically at alpha radiation and beta radiation and positron emission, all three of these. Starting with alpha. So alpha emission occurs when the nucleus of my atom releases an alpha particle. So for instance, uranium-238 can decay by alpha emission, and it's going to look like this. So uranium has a mass of 238, has 92 protons. If it decays by alpha emission, we get an alpha particle ejected from that nucleus. And what's left behind, oops, is a thorium nucleus when it decays by alpha emission. Now what I want you to notice on alpha emission, as well as every other nuclear reaction that we do in this class, is that mass is always conserved and positive charge is always conserved. So on this side we have 238 as our total mass, and on this side we have 4 plus 234, which adds up to 238. Everybody see that? So this is important. Mass is conserved. Okay, next I want you to also notice here we have 92 protons or 92 positive charges, and on the right hand side we have 2 plus 90, so I got 92 positive charges. So my charges are also conserved. And that's true of all the reactions that we do. So I could tell you that something's going to decay by alpha emission, and you can tell me what's going to be formed. You can predict just using some really simple math, right? So if I told you that polonium-208 decays by alpha emission, then you know it's going to form an alpha particle. And you can tell me what else is going to be formed. What's the mass that will be formed? $204, right? Because 204 plus 4 is going to give me 208. Okay. What is the bottom number here, the number of positive charges? 82. And once we know it's got 82 protons, that defines my element. What element has 82 protons? Lead. Just look it up on our handy dandy periodic table. See if I can remember where that is. Is that here? Yep, 82. Lead right there. That's it. Was that easy? Do you guys think you can do that in an exam type setting? Now, just to be fair, I might not write the whole thing out and say fill in the blank. I might say polonium decays by alpha emission. What else must be formed? Right? And then you have to be able to set up this equation this way. Remember that emission means I'm losing it, I'm emitting it. So this is part of a product of alpha emission, alpha radiation. Okay, or the products. But yeah, that's alpha emission. There's not any more or less to it than that. Let's try beta emission. So this is alpha. Beta emission is funny. You might say, hey, I just told you that a beta particle was an electron. And we know that electrons exist in the cloud surrounding the nucleus and not in the nucleus. So how could I have nuclear decay where my nucleus appears to be losing an electron? That's weird. Is that weird? You guys bothered by that? You should be bothered by that. I'm telling you, this nucleus lost an electron. You are bothered now. Well, here's the funny thing. So with nucleus, we typically think of having just protons and neutrons. But, and that's how we introduced it to you, But the question then is, what are protons made of and what are neutrons made of? It turns out if we lose an electron from the nucleus, we'll discover that a neutron has been converted into a proton if I lost the electron. So these particles, protons, neutrons, more complicated than individual whole pieces. They appear to be these complexes of teeny charged particles like electrons and positrons. So we can see if I take a neutron which has a mass of 1 and a charge of 0, and if we lose an electron which has a mass of 0 and a charge of -1, it's converted into a proton which has a mass of 1 and a charge of +1. And I hope you see, again, mass is conserved because 1 is the same as 0 plus 1. And charge is conserved because 0 is the same as -1 plus a +1. So the neutron essentially is converted into the proton and the electron is kicked out. Everybody following what appears to be going on here? Essentially, we originally talked about, protons and neutrons like they were whole particles, but really protons are these conglomerations of tiny particles, and so are neutrons. And neutrons have electrons in them, and if I lose an electron, then I've converted that neutron into a proton. This is important because we talked about last week how the stability of your nucleus depends in part on your ratio of neutrons to protons. So if you have too many neutrons, then one convenient way to change that balance is to just convert one into a proton. Then you have a higher proton to neutron ratio. So, but you can follow your mass, 1 equals 0 plus 1, and your charge, 0 equals -1 plus a +1. And we're not going to view it like this. We're going to see it from the perspective of a whole atom, whole atom, right? Not just a single neutron, because we don't have neutrons running around doing beta emission. We have atoms doing this. So for example, and maybe this will make more sense when we see it here, iodine 131 reacts by beta emission. So iodine 131, and it's number 53. So when we see beta emission, then you know we're losing an electron. So it might be shown like that, or it might be shown like that, maybe like this, depending on how Master Chemistry wants to do it. I will always show it like this. Electron. And the other species that forms is going to be xenon 131. Now, follow me here. Was the mass and the charge conserved on this? Yes. Yep. Hang on a second. I don't actually need that little negative charge because it's right here. Show us a negative charge. But yes, we have 131 on the mass on the left, and 0 plus 131, that's 131 for the mass on the right. We have 53 for the total positive charges on the left. And we have -1 plus 54 for the total positive charges on the right. So just like alpha emission, we can do a little simple arithmetic, and you guys can predict what else might be formed by beta emission from the nucleus. So for example, if I told you carbon-14 decays by beta emission, what else would have to be formed from that equation? nitrogen. So you guys saw, so 14, it'll still be 14. And then 6 equals -1 plus 7, and element 7 is nitrogen. Perfect. Can you guys do that one on an exam type setting? Again, I might say fill in the blank, but I might say, I might just use words to describe what's going on and say carbon-14 decays by beta emission. What else must be formed? And you might have to come up with this equation. Let's do 10 of these on the test. They're kind of fun. I mean, it's so simple compared to the math that you've had to do with the acid and base chemistry. Am I right? Kind of relaxing in comparison. Okay. Next, we've got positron emission. And I told you that the positron is like an electron, but it has a positive charge. So it has a mass of 0 and a charge of +1. Now, again, you're going to say, well, we never talked about positrons existing in the nucleus. So where does the positron come from? It's one of the particles inside your protons and your neutrons. So what would happen if your nucleus lost a positron? Do you think that would come from your proton or from your neutron? I think the test has like 21 questions or so, Candace. That's right, the positron comes from the proton because they're both positively charged. Excellent. So if we've got a proton which has a mass of 1 and a charge of 1, and it releases a positron which has a mass of 0 and a charge of 1, what would be left behind? If you just do the math, that'll tell you. So initially you had a mass of 1. You haven't lost any mass, excuse me. So you still have a mass of 1. Initially you had a charge of 1, but you did lose a charge of 1. So what you've got left is a charge of 0. What particle has a mass of 1 and a charge of 0? The neutron. Neutron. Mass of 1, charge of 0. Okay, so essentially positron emission is the opposite of beta emission, because beta emission converts a neutron into a proton, positron emission converts a proton into a neutron. So both of these are used to kind of help balance out our proton-neutron ratio here. So for example, potassium-40 decays by positron emission. To make argon-40. This is interesting, by the way. I think potassium-40 is the most stable form of potassium, but it is radioactive. All forms of potassium are radioactive. So everybody gets a little dose of radioactivity every time they eat potassium, like measurable radioactivity from eating bananas, for instance, which is kind of fun, kind of scary, depending on what perspective you're looking at it from. But just a low level meets background radiation, not a big deal, kind of fun. But note here, okay, total mass on the left, 40 equals total mass on the right, 0 plus 40. Total charge on the left, 19 equals total charges on the right, 1 plus 18. Everybody following that? So we could again predict this. If I told you that carbon decays by positron emission, you could tell me what else is formed. Am I right? Yeah, it still has a mass of 11. Now it's going to have a total of 5 positive charges, and then element number 5 on the periodic table is boron. You guys feel like you can do that on the exam? All right, well, you guys said you wanted 10 like these. Let's look at our in-class activity sheet. And that's exactly what section 2 is asking for, except there's 12 instead of 10. Again, these numbers are offset. They shouldn't be offset. They should be stacked, but that was what Word was going to do for me, so that's what we got. So the key then is to fill in the blank and then also identify by what you see here whether we're looking at alpha emission or positron emission or beta emission or what. Oh, you want 10 on the test? I figured I'd just give you, maybe 1 or 2 on the test. 10 to practice. Just like I did up here, right? Let's see, what is that? 10 to practice, 1 or 2 of each of these on the test? Pretty standard. You guys. Okay, so help me out with this top one here. What type of emission is occurring? Yep, this is alpha emission because this is your alpha particle. That's how you can tell. Lost an alpha particle. So what else is going to be formed when platinum 190 decays by alpha emission? Perfect. Perfect. So the first thing you do is determine what the new mass is going to be, 186, and then determine what your new charge, total positive count, is going to be. In this case, 76. And then you just look up number 76 on the periodic table, which happens to be osmium. Okay, let's try this one. What kind of emission is this? Positron or beta plus. Excellent. And what else is going to be formed? So you know it's going to have a mass of 74 and then 32 protons. That makes it germanium. Excellent. Okay. And then what is this going to be? Oh, you guys, way ahead of me. Hang on a second. This is beta emission, beta minus, or what we just call beta. If I didn't say beta plus, then it would be assuming it's beta minus, and that's going to be mass of 32, 16 positive charges. That makes it sulfur. Awesome. You guys are professionals, okay? Do remember that for each of these emission, that beta particle, that positron, that alpha particle are products. They're being emitted, kicked out from the nucleus. Okay, because if you accidentally put it on the wrong side, then you get the wrong answer, right? Okay, you guys feel good about that? Okay, one last fun thing before we go to note here. Alpha emission and beta emission were the first 2 types of radiation that were discovered. Because they're actual physical particles and they have charges and they have mass that we can kind of track, which was kind of interesting. We don't actually ever see positron emission because the positron is the antiparticle to the electron. This is electron antimatter. So when the positron gets ejected from the nucleus and it encounters an electron, which it does as it's leaving the atom, because the atom has a shell of electrons, then the positron and the electron are simultaneously destroyed and converted into pure energy. So instead of actually seeing the positron, we'll end up seeing gamma radiation emitted from your atom, because the positron that was produced was immediately annihilated by an electron that it encountered, which is kind of cool, I think. When you think of antimatter as like a Star Trek-y kind of thing. But no, it's real. And I think that's kind of fun. Anyways, that and you guys are radioactive because you guys eat bananas. So I'm going to stop this recording. We're going to start another.